Okay, let's look at a couple of problems to review for our Module 6 test. So Module 6 talked a lot about the composition, inverse functions, then talked a lot about our exponential equations and how we solve those. So this first question says, given these two functions, f of x equals x squared minus 9 and g of x equals x plus 3, first find f of g of x and then find f of g of 3. So if we find f of g of x, this is where we're going to put one function into the other. We're going to put g into f. So everywhere I see x in the f function, I'm going to put this whole entire thing of g. So in this case, it says x squared, but instead of x, I'm going to put square root x plus 3 squared minus 9. So everything that was just an x is now this square root of x plus 3. Now, we remember that the square root and the square will cancel out, so that will just leave us x plus 3 minus 9. And then 3 minus 9 is just negative 6, so this is just x minus 6. Now for the second part, f composed with g of 3, once you have the first part, this is really simple. Because all this says is, instead of x, I want to put a 3. So this just means x equals 3. So this is just 3 minus 6, which is just negative 3. So anytime you have a value there, 3 or 4, whatever, you're going to get a number. Okay, let's look at number 2. Find the inverse function of h of x equals 3x minus 8. Well, when we're finding the inverse, if you remember, this is where we switch x and y. But of course, in this problem, there currently is no y. But h of x, that function notation, can just represent y. So this would just be y equals 3x minus 8. So now if I switch x and y, I'll get x equals 3y minus 8. And now I can just resolve for y. So I'll add 8 to both sides. So x plus 8 equals 3y. And then I'll just divide everything by 3. So we get x plus 8 over 3. So this is my inverse function, which if I want, I could denote h inverse x. Same thing. All right, let's look at number 3. Number 3 says, are the functions f of x, g of x, inverse functions? Well, we know things are inverse functions if their compositions, f composed with g of x and g composed with f of x, are the same and they both have to equal x. So they don't just give you x, either one of them, then it is not a inverse function. So start with f of g of x, where I'm putting g in for f. So our f function is x squared minus 9. So instead of having the x, I'm going to put the g function, which is square root x plus 9. So now if I square the square root, I get x plus 9, because those cancel, minus 9, which gives me x. Now, that is not enough to say they're inverses. This is half of what we need, but we also must do g of f of x. So if I do that, I'm plugging the f into g. So if I do that, I have the square root of x plus 9. Well, now instead of that, I'm going to put in x squared minus 9. So this took the place of the x. Well, you can see the 9's go away. So really all we have is the square root of x squared. And just like we said earlier, the square and the square root will always cancel out. So this just gives us x. So we could say, yes, these are inverses. Okay, let's look at this last one on this first page. What is the domain, range, horizontal, and vertical asymptotes of the function 3 to the x minus 7? Now you could graph this on Desmos, and I would suggest you do this. I'll just kind of put a sketch of it here. So it's going to look something like this if I graph it. Okay. Now the key thing for doing domain and range and everything else is this number that comes after it, which in our case is -7. Now the domain for every exponential function, doesn't matter, is always negative infinity to infinity. That is for every exponential. Now the range is typically 0 to infinity, but you can see how this one is shifted down, so this one starts kind of flattening out here at -7. So the range is actually -7 to infinity. And whatever this number is up here, that number you add or subtract, that's going to basically move your range up or down. Horizontal asymptotes, there is one, and it's always this same number, this important number we're talking about. So the horizontal asymptote is -7. As for vertical asymptotes, this never actually goes straight up, so there are actually none. There are never any vertical asymptotes for an exponential. So this and this should always be the exact same for every problem. And this should always match. Okay, the second page has a lot of different kind of problems where we use the exponential law or we use our properties of logs to solve equations. So just recall our properties of logs. We said if we have b to the x equal y as an exponential equation, that is the same as the log base b of y equals x. So we have this rearrangement where the exponent in the exponential goes by itself, the base goes to the base, and whatever was by itself in the exponential goes to be your value of the log. So if I look at this first problem, 4 to the x plus 1 equal 256, it's an exponential, so I can turn it to log. So whatever is the exponent will go by itself, so that's x plus 1 in this case. And this would be log base 4 of 256. Now I don't know what that number is, but if you recall how to put that in the calculator, this would be log 256 divided by log 4. So that is just going to turn out to be 4. So we have x plus 1 equal 4. I'll subtract 1, so x equals 3. So this conversion formula is very important, and also remembering how to put the logs in the calculator, very important. Okay, let's look at number 6, which says 8 to the x equals 7. Very similar kind of problem, where we'll change it to log form. So the exponent goes by itself, x. This is log base 8 of 7. So this would be log of 7 divided by log of 8. So if I do log of 7 divided by log of 8, I get some random decimal. We went around to the nearest hundredth, which is 2 decimal places. So that'd be 0.94. And make sure when you're going through this review, you're actually putting these in the calculator, making sure you're getting the same numbers as me, because that's one of the things that you can mess you up on the test. Okay, our next couple are some log equations that we're just going to switch to exponential form to solve. So we have log base 4 of 2x plus 1 equals 2. So if I switch that to exponential form, that's 4 to the second equals 2x minus 1. It's just the opposite. It's the base to this power equals whatever this is. So 4 squared is 16 equal 2x minus 1. I'll add 1 to both sides. So 17 equals 2x. And then I'll divide both sides by 2. So x is 17 over 2. So I can't stress how important that change of forms is, where you're going from log to exponential or exponential log. Very important. Okay, let's look at number 8. Now in this case we have 2 logs n equal to a number. But if you recall, when you have 2 logs that are added together, we can make this 1 log by using our property that says 2 logs added together is just the product of the 2 things in the log. So I just multiplied x and 3, got 3x. So we have log base 2 of 3x equals 3. So if I change forms, I get 3x equals 2 to the 3rd power. Again, same thing. Base to this equals this. So 2 to the 3rd power, 2 times 2 times 2 is 8. So I'll divide both sides by 3. So x is 8/3. Okay, problems 9 and 10 deal with trying to use the property of logs. So those are when you have a number out front, we make it an exponent. When you add 2 logs, it becomes multiplication. When you subtract 2 logs, it becomes division. So on this first one, the thing I noticed first is this 5 out in front. Any number that's out front can be put up as an exponent. So I can rewrite this as log x to the 5th minus log of 10 plus log of 8. So these 2 logs, the log x to the 5th and the log 10, are subtracted. That means I will divide them. So write it as a single log. It'll be x to the 5th over 10 plus log of 8. But now when I add 2 logs, adding 2 logs means I will multiply them. So I can write this as 1 log. Now you can think of this as 8 over 1, so the 8 really just multiplies to the top. So 8x to the 5th over 10. This would be a good answer. I can actually reduce my fraction because 8/10 reduces to 4/5. So I can actually make this log 4x to the 5th over 5. These logs didn't have a base listed. It was just the generic base 10. But if there was a base, you just keep the base the same throughout the problem. Okay, this next one actually deals with the ln, or the natural log. So we'll take this 3, we'll put it up top. We'll take this 5, we'll put it up top. We'll take this 2 and put it up top. So this will give me ln x to the 3rd minus ln x to the 5th minus ln x to the 2nd. So these first 2, if I divide, I'll get ln x to the 3rd divided by x to the 5th minus ln x to the 2nd. So I'm going to divide again, and when I divide a fraction by a number, I just know that I'm multiplying by the reciprocal, so instead of x squared over 1, it's 1 over x squared. So the x squared would just go on bottom. So I have ln, I have 3 x's on top and 7 on bottom. So I can actually cancel 3 of these and leave 4 on the bottom. So this is ln 1 over x to the 4th. Okay, the last thing we talked about was some of these kind of word problems where we were setting up growth and decay equations. So number 11, 12 deal with this problem. It says the number of quality math teachers is declining in America. The number of teachers declines at a rate of 8.7 per year from 189,000 in 1980. So in 1980 there were 189,000 and we reduced by 8.7% every year. So if you remember the generic, this is decay. Y equals A, 1 minus R to the X. Now in this case, X is going to be years after 1980, because it starts in 1980. And so Y is the number of quality math teachers. So if I plug these numbers in, I get Y equals 189,000, because remember, this is always your initial value. 1 minus the rate, so that's 1 minus 0.087, make sure you put it in decimal, to the X. So if I subtract that, I get 189,000, and I get 0.913 to the X. So this is my equation I can really solve anything I want for. Now in question 11 it says, how many will there be in 2020? Well, if we start in 1980 and we're in 2020, that would be 40 years afterwards. So we are saying the years is 40, so we're saying X is 40. So all I have to do is plug 40 in for X and I'll get my math teachers. So 189,000.913 to the 40. And if I put that in the calculator, I get 4957.8, we'll just say 58 quality math teachers. Okay, number 12 is looking at a little different type of problem, although using the same equation. How long until there are 100,000 quality math teachers in America? Well, that's talking about the number of teachers, which if we look up here, that was Y. So really what we're trying to do is if Y is 100,000, what would X be? Now remember from above, the relationship here is Y equals 189,000.913 to the X. So I'm just going to plug in 100,000 for Y. So 100,000 equals 189,000 times 0.13 to the X. I would divide both sides by 189,000, very similar to the problems we've done before. So 100,000 divided by 189,000 is 0.53 if we go to 2 decimals. So that's 0.53 equals 0.913 to the X. And so now to get the X by itself, we'll change it to log form. So X is going to equal log of base 0.913 of 0.53. So we put that in the calculator as log of 0.53 divided by log of 0.913. Which in this case would give 6.975, so we'll say 6.98 years. So almost 7 years to decline from 189,000 to 100,000. Okay, so we're going to look at how we do 13 and 14, which use the compound interest formula, which if you recall is A equals P 1 plus R over N to the NT. So in this problem, we're just really plugging in some values. We have a rate of 4, compounded quarterly, so that's N. We initially deposit $400, and we leave it in there for 5 years. So really, we're just plugging numbers in. So the principal is how much I start, that's 400. 1 plus the rate, which is 0.04. Compounded quarterly, which would be 4 times. To the NT, which would be 4, and the T is 5. I always like to put those in parentheses just to make sure it works out right. So go ahead and plug that in your calculator, but I get 488.0, we'll round it up to 8. So in 5 years we make $88 for not really doing much. Okay. So the second one is really similar, except for we're going to try to find the time. So we have $12,000, which is our principal, which we are trying to put in an account with an 8% rate. Compound is semi-annually, so that'll be our N. How long until the money is doubled? So in this case, we don't know what T is. So if we look at our formula, A equals P 1 plus R over N to the NT. Well, we start with 12,000. We have 1 plus 0.08. Semi-annually would be twice. It would be to the 2 for N. And then T we don't know, so I'll put T there. And we want this nut money to double. So we want this to equal 24,000. So we want the amount in the account to be 24,000. So this is the equation we must solve. So this is obviously going to be one of the ones where we're going to go backwards and we're going to use our logarithms. So first divide by 12,000. So we'll get 2 equals all this stuff to the 2t. So all this stuff in here I can just put in the calculator. And I get 1.04, because 0.08 divided by 2 is 0.04, and then add 1. So then I can change it to log form. So the exponent 2t will equal log base 1.04 to the 2. And so if I put that in the calculator, it's 2t equals log of 2 divided by log of 1.04. So that's going to give me 17.67. I'll say 17.7. And then I'll just simply divide both sides by 2. So if I divide that by 2, I get 8.835. So we'll say 8.84. And that would be years. So it's going to take about almost 9 years for our money to double. All right, hopefully this was helpful. Please let us know if you have any questions before trying the test.